Firstly, I'd like to thank the organisers for giving me the opportunity to present our work, which is basically, I'm going to give a review of high power mid-IR laser systems, femtosecond laser systems, I should add, for Attosecond Science and Spectroscopy. My name is Mark Prandolini. I'm co-founder of the laser firm Class 5 Photonics, and I also work at the University of Hamburg in Germany. So this will be a fairly introductory talk. So for the experts in high power mid-infrared lasers, it might be a little boring, but for the rest of the audience, I hope to give you a flavor of what's happening and that you can give a sort of comparison for what's going on in the latest of high power mid-infrared lasers. I'll want to begin the talk with talking about applications in spectroscopy. Then I want to explain what does mid-infrared laser systems with wavelengths with periods of tens of femtoseconds to do with attosecond science. And then I will present a review of two high power systems that are currently being built by Class 5 Photonics, and then compare them to what's going on in the world so that you get a general review of how you would build such a laser and what's the state of the art of these laser systems. So let's get started. Firstly, why might you need high mid-infrared femtosecond laser systems? So in the area of molecular physics, there are many biomolecules that have their resonances in the so-called mid-infrared region. In particular, there's this famous fingerprint region somewhere between 6 and 14 micrometers. I'm just using my mouse now to sort of pinpoint. Can everyone see my mouse? It's from 6 to 14. Is that clear to everybody?
Yes.
Good. So that's one reason, molecular physics. Another reason would be solid state physics. And I've got an example here on the bottom right-hand corner of a resonance of a Dirac plasmon in graphene, which is quite a topical topic at the moment. The particular resonance actually is around 9 micrometers. There are other resonances in solid state physics, including polarons, Landau level transitions, magnons and phonons. So there's lots of scientific reasons to do mid-infrared spectroscopy. The next question I want to introduce is why might you need high average power? Now, just to explain, for a pulsed laser, the average power is the pulse energy times the repetition rate. But that's not the only important parameter. It is the peak power, which is you take the pulse energy again and you divide it this time by the pulse duration. Now, if the pulse duration is in the femtosecond area, the peak power will be incredibly high. So I just want you to keep in mind these two notions of power. The average power, which will be around the watt to tens of watts level, and the peak power, which can be anywhere into the petawatt area, 10 to the 12, 10 to the 15. So the first application where you need high average power and high peak power would be imaging, especially imaging involving 2 photon and 3 photon absorption, which requires high intensity lasers. And you need the high intensity to achieve enough signal to noise for each pixel. And then you need to cover the whole image. So that's where you need a high repetition rate. So you need to combine high average power with high peak power for such an image. Another application would be 2D mid-infrared spectroscopy. I've got a little scheme of the laser setup, which is typical of the laser setups that we use. They take a ytterbium solid state laser, which is a femtosecond laser, and it produces an output of 1 micron. And through a process of optical parametric amplification, they can convert the 1 micron into the mid-infrared. Then you've got mid-infrared pulses. And then to scan the image that you can see at the right-hand side there, here, you need a high repetition rate to cover the experiment within a reasonable time. So that's why you need high average power mid-infrared lasers in the femtosecond region. The next application is Attosecond Science and Soft-X-rays, enabled by MIR-IR femtosecond laser sources. Now, at the first thought, what does mid-infrared lasers got to do with attosecond science? If you look at one period of a mid-IR laser, we're looking at somewhere between tens of femtoseconds. So that's nowhere near attosecond or soft X-rays. However, in 1987, there was a process called high harmonic generation, HHG, where usually in those days, a driving laser in the near infrared region was produced using high harmonic generation, a much higher harmonic, which reached down into the EUV, that is the extreme ultraviolet, or into the X-ray, soft X-ray region. Let me explain experimentally how that occurred. You take your driving laser, it's a femtosecond laser, you focus it down into a gas cell. The gas was usually helium, neon, or argon. You then filter out the driving laser and you're left with a train of attosecond pulses. In fact, if you design the driving laser and focusing scheme carefully, and you design the target carefully, you can achieve a single attosecond pulse for a single femtosecond driving pulse of the mid-IR laser. Now, our particular application is we want to achieve attosecond laser pulses into the water window. Now, the water window is defined as the K edge of carbon at 4.4 nanometers to the K edge of oxygen at down to 2.3 nanometers. And the dream application we're looking at would be live cell imaging with femtosecond time resolution. So just to summarize this process of high harmonic generation, it was discovered in 1987, understood as a sort of single atom approach. That means your single helium atom acts as a little antenna. The electron is ripped out by the mid-IR, comes back down and produces either the EUV, extreme ultraviolet, or soft X-rays. And now you can get commercial HHG sources up to the EV range. And Class 5 produces a Moonlander HHG with the parameters given below. So that is one very important application of femtosecond mid-IR laser sources. Continuing on with this theme of attosecond science driven by mid-IR lasers, I've taken this diagram from a Nature Photonics article 2010. And on the x-axis, you see the driving laser wavelength. Now, we start at 0.8. That was the sort of femtosecond lasers of the second generation. They're all TISAF lasers, which produce wavelengths at 800 nanometers or 0.8 of a micrometer. And as you can see from the y-axis is the produced higher harmonic from the HHG. So at 0.8 of a micrometer, you can only achieve extreme UV radiation. To get into the water window and beyond, you need to increase the wavelength of the driving laser. This has been shown theoretically as well as experimentally. So we hope to produce a laser system at roughly somewhere between 3 and 4 micrometers and get well beyond the water window into the soft X-ray range, producing attosecond pulses, again through a process called HHG. So I hope that explains how mid-infrared lasers are used to produce attosecond pulses as well as soft X-rays. Continuing on with my review, I mentioned in the last slide that at least for the last 20 years of femtosecond science, it was largely driven by TISAF lasers. And let me just give you a rough laser description, how that works. And there's an associated Nobel Prize in 2018 for the Chirped-Pulse amplification. You start off with an oscillator, which is also a TISAF laser system. You stretch the pulses. You then pump it in a traditional TI-sapphire amplifying system, and then you compress the pulses. That's the CPA, chirp, amplification, and compression. This workhorse for femtosecond technology for the last 20 years is often called the second generation of femtosecond lasers. It was limited to 20 femtoseconds. As I mentioned before, had a fixed wavelength of 800 nanometers or 0.8 of a micrometer. It was, it could be actively CEP stabilized. I won't explain what all that means. CEP means carrier envelope phase stabilization. There's another associated Nobel Prize in 2005 for the frequency comb using CEP. So CEP is important for these laser systems. But this second generation of TISAF lasers had a disadvantage. Not only was it fixed wavelength with limited pulse duration, but it also had a small gain for every single path. That means the laser systems were large and complex, and over 40 watts required extensive cryogenic cooling. So what was the solution to the second generation? Well, it was the third generation. And the third generation of femtosecond lasers is often called optical parametric chirp-pulse amplification. So the chirp-pulse amplification remains, but what we do is we replace the amplifier crystal. Just wait, I'll use the mouse. We replace the traditional amplifier with a nonlinear crystal with a process called optical parametric amplification, where you have a pump wave. Usually that's from a separate laser, and the pump wave transfers energy into the signal and the idler waves via a second order process in the nonlinear crystal. As I mentioned before, the CPA part remains, but we've replaced the amplifying crystal. This third generation of femtosecond lasers, called OPCPA, is reviewed in a review article in Optical in the first volume. These systems can achieve pulse durations under 10 femtoseconds. They're wavelength tunable, so everywhere from UV to terahertz. They can be passively CEP stabilized and have the advantage of a high gain in a single pass through the crystal. That means these laser systems are compact, and the next advantage is they have minimal heat dissipation compared to conventional lasers. Now, I've got one more slide where I compare a conventional laser amplifier with an optical parametric amplifier, just to sort of complete this review. So, for this conference, I assume everyone knows what a conventional laser is. You have energy levels, and on the left-hand side, we see energy levels for a ytterbium in YAG as an example. The pump laser is used to bring electrons from the ground state into the excited state. So energy is now stored within the crystal. The electrons from the excited state decay to the laser transition, giving off heat. And then you have the laser transition. Now you can put this system either in an oscillator or use it as an amplifier. Now the same applies to an optical parametric amplification system. As I mentioned in the last slide, you have a pump, a signal, and an idler. And the process is done in a nonlinear, transparent dielectric crystal where we use the properties of the second order processes, second order nonlinear processes. Now we have to fulfill energy conditions. That means the pump frequency must equal the signal plus the idler, and the pump transfers energy via the second order process into the signal and idler waves. I've drawn the energy levels as dashed lines just to indicate that there are no transition of electrons being evolved here. This is a second order nonlinear process, and so no heat is absorbed. Sorry, that's not exactly true, but no energy levels are changed in this system. So no major heat is stored in the crystal. That's possibly a more accurate statement. Okay, that brings me to how does Class 5 build a rough scheme, our high power OPCPA lasers. We begin with a pump laser, a conventional pump laser based on ytterbium solid state. It produces roughly 1 micron, or more accurately 1030 nanometers, and has pulse durations. It's quite narrow band actually, and has, compared to broadband femtosecond lasers, and has pulse durations around the 1 to 2 picosecond. So we take we beam split a small section of this pump laser and create the seed. Instead of in an oscillator, we create the seed in a white light generator, which I'll talk about in the next couple of slides. And then we have the traditional CPA, stretching, amplification, and compression. As I mentioned before in the last slide, the amplification is now achieved in an optical parametric amplification. And the whole process is called OPCPA, Optical Parametric Chirped-Pulse Amplification. So let's quickly review the conventional pump lasers, ytterbium-based. As I mentioned before, conventional laser systems produce a lot of heat. So you've got to get rid of this heat. How do we do it for really high powers? Well, there's 3 traditional geometries. One is to use a cylindrical system. That's sort of like a fiber laser, where you cool the outside of the whole cylinder. A second geometry would be an inner slab, where you have your gain material in the middle and you have a heat sink above and below. The disadvantage of this system is that you've got a differential thermal lensing in one direction compared to the longitudinal lensing, longitudinal direction. However, with the InnoSlab technology, they use this disadvantage to an advantage. And then the third variety is a thin disc amplifier, where you take a thin disc of a gain material and you cool just one side. This allows for a very uniform temperature across the gain material and very little thermal lensing. And this system often achieves very high pulse energies. So the typical wattage for each of these systems is described below, and they're the three varieties of ytterbium-based pump lasers that Class 5 uses. Next theme I want to address is we've thrown away the oscillator, so the seed is generated in a process called white light generation. Just to explain what that is, we take a small part of the pump laser and we put it through a ytterbium YAG, sorry, no, not ytterbium, we put it through a pure YAG crystal, I should say. It then forms a filament and produces coherent laser light right from 600 to 1.5, 1.6 micrometers. And we use this light as a seed for our laser systems. Okay, so this comes to the part of the talk where I now review two mid-infrared laser systems produced by Class 5. The first one is a tunable system from 4 to 11 micrometers. This was done in collaboration with DAISY, which is a Helmholtz Institute here in Hamburg, and partially financed by the IFB Hamburg. As I mentioned, it's tunable. It reached powers of 440 milliwatts with a pulse duration of 80 femtoseconds at 9 micrometers, repetition rate of 200 kilohertz. Yes, it could be CEP stable. The nonlinear crystal that we used is LGS, and our envisaged application is biomolecular spectroscopy. The second system that I want to present is at 3.2, and this is in collaboration with a European consortium called ELI, which is for Attosecond Science. Now, this system will be 25 watts, pulse durations under 50 femtoseconds, with 1 kilohertz repetition rate. Yes, it'll also be CEP. The nonlinear crystal used will be KTA, and the main application will be generating attosecond pulses in the soft X-ray region using HHG, as I explained before. So I'm now going to show experimental results from our tunable system, the 4.2 to 11 nanometers. So that's the first system I'm going to talk about. This system here. So here's a basic diagram of how this laser is put together. So let me explain it. We begin, as I mentioned before, with a ytterbium YAG pump laser, producing a narrow band 1 micron output. This particular laser was an InnoSlab, one of the 3 varieties that I showed you above. So we have a white light generation. This white light is then, so it's a Chirped-Pulse amplification scheme. So we have to firstly stretch the pulses. They could be stretched either in material, SF11, or we could use chirp mirrors. We've done both with this system. We amplify the seed, which was from 1.1 to 1.3 micrometers, in a non-collinear optical parametric amplifier. Let me apologize for introducing now more acronyms, but hopefully I can explain that, which is just a broadband optical parametric amplifier, and it's tunable. And now we produce the MIR-IR by a process called difference frequency generation. All these processes are second order non-linear processes, all involving pump, signal, and idler. So in the DFG, we are interested in now the idler wave. And if you can look at that last little frequency at the bottom here, if the pump frequency minus the signal frequency are sort of similar, you can reach the mid-infrared wavelengths if you've chosen the crystal correctly and it's transparent in those regions. So the final pulses are produced in the mid-infrared from 2 to 4, and we have a broad band at 9 micrometers. The pulses are compressed in zinc selenide. There's a beam splitter, final beam splitter, splitting out the mid-infrared to the pump and idler, from the pump and signal waves. So they go into the beam dump, and the beam splitter lets through or separates out the idler signal, which is the MIR-IR. Here's some experimental results. As you can see on the left-hand side, it's tunable from 4 to 11. And in the middle, well, not quite the middle, but round about 9 micrometers, we have a nice broadband pulse. On the right-hand side, you can see that across most of this range, we have pulse energies above 1 microjoule. That little dip in the middle between 6 and 7 microjoules is because of water vapor. That can be eliminated by purging our laser systems with an inert gas, so that shouldn't be a problem. And we achieve efficiencies over 1% from between 8 and 9 micrometers. The deficiency is defined as the pulse energy of the pump to the final MIR-IR pulse energy. That's how we define efficiency. Okay, so let's review a little bit more. If we look a little bit more closely at this broadband pulse at 9 micrometers. Again, we used 40 watts at 1 micron. That was the pump. And we produced 440 milliwatts at 9 micrometers. Pulse energy is 2.2 microjoules at 200 kilohertz. As I mentioned before, efficiencies a little bit over 1%. Now, this particular pulse has a Fourier limit close to 70 femtoseconds. So we compressed the pulse and we measured the pulse duration, which I'll show you in the next slide. Now, to measure the pulse duration, we used a cross-correlation experiment, and deconvoluting the cross-correlation experiment, we determined that the pulse energy is very close to 80 femtoseconds, with a Fourier limit of 68, as I mentioned before. The very good fit here between the cross-correlation and a Gaussian fit indicates that higher order dispersions are sort of under control or somewhat minimized. So we have produced a pulse very close to the Fourier limit. The next question I might ask is, well, that was 0.4 of a watt. How far could what are the power limits at 9 micrometers? So what we did is we decided to do a material study published in Optical Materials Express of all the important lithium-based nonlinear crystals for high power MIR-IR OPCPA pumped at 1 mu under realistic operational conditions. There's the list of crystals we investigated: LGS, LGSE, LIS and LIS-E, and we measured the nonlinear refractive index, the linear absorption, and the nonlinear absorption. And through simulations, based on the results derived from this paper, we predict we should be able to, if we were to pump at 200 watts with a ytterbium InnoSlab pump laser, we should be able to achieve over 2 watts at 9 micrometers, which corresponds to 2.2 microjoules at 1 megahertz, and maintain pulse durations under 100 femtoseconds. Okay, I've now explained this 9 micrometer. It's also tunable. So how does this compare to the state of the art that is currently available? So I've made a list of various systems. If you want, you can get the list of references from me. I can supply them to you, just write to me. But the top line is this work here, done by Class 5 in collaboration with Daisy. So our tuning range is relatively comparable to other tuning ranges. Some laser systems are just fixed wavelength. Our pulse durations are also quite competitive compared to other systems. Our pulse energy is very good. Now, there's some very high pulse energies towards the ends of this table, but they have other disadvantages in pulse duration, as you can see. And presently, we're achieving somewhat like 440 milliwatts. But from the previous material study that I showed you above, it should be possible to achieve over 2 watts at 9 micrometers. And that would be then a world record for this particular laser system within the femtosecond region. Okay, so that gives you a feel for mid-infrared femtosecond laser systems at the sort of around 9 micrometers. Now let's switch track a little bit and go down to 3.2 micrometers. Now this is the second system I want to talk about. It's in the planning. We haven't got any experimental results, so I only present 2 slides or 3 slides on this. This is a system that we're going to build for ELI, which is a European consortium for Attosecond Science. This is a picture of the signing of the contract. And our aim will be to produce attosecond pulses with wavelengths shorter than 1 nanometer through a process of HHG, as I explained at the beginning of the talk. And the crystal we're going to use is KTP. This is a nonlinear crystal which is suitable for producing 3.2 micrometers. So I'm just going to present one slide about the laser architecture that we're proposing. So it's going to be a high energy system at 3.2 for ELI, based on KTP. The chosen ytterbium-based pump laser is going to be a thin disc. That was one of the 3 varieties that I showed you above, with a narrow band of roughly 1 U output. So this pump laser has 200 watts, 200 millijoule pulse energy, 1 kilohertz, and will have pulse durations under 6 picoseconds. So we're going to pick off 4 millijoules of this pump laser and put it into a standard product from Class 5 called a White Dwarf 3000. Now the output of our standard sort of product from Class 5 will then go into a booster, which hasn't been built yet but is in the planning. This takes the rest of the pump energy, which is the majority of it. The material used will be KTA. Then the pulses will be compressed down to 50 femtoseconds, 25 millijoules at 3.2 micrometers. So that's the general scheme of this laser system. And now the question is, how does that compare with the state of the art. And here it is here. Again, I should say that the list of references I can supply if anyone's interested. But on the x-axis, we have repetition rate, and on the y-axis, we have pulse energy. And the system that I just proposed at 3.2 microns is up there, just above the sort of 10 watt line. It's at 25 watts, as I mentioned before. The other systems in red are other laser systems that Class 5 has produced for various customers. So as you can see, we're quite experienced in producing high power lasers in the close to mid-infrared region, and our proposed system is a high energy system. So with that, I'm coming close to the end of my talk. I want to sort of bring home a few take-home messages. I've talked about femtosecond lasers in the mid-infrared region. I've shown that at the sort of lower end, that was the last laser that I presented, you can get tens of watts, up to 100 watts maybe. And at the upper end, say 9 microns, you can get to the watt level with femtosecond lasers. This is all achieved with what is now called the third generation of femtosecond lasers, OPCPA. So with that, if you want to know more, please get into contact with us. You can either contact the firm directly at info@class5photonics.com or contact me directly, Mark Prandolini at daisy.de. I thank you for your attention.